Hello everybody, welcome back to our discussion on quasi-geostrophic theory. Today we'll be tackling an application of the equations that we described from last time, and we'll be looking at large-scale or synoptic scale waves in the atmosphere. So these type of waves commonly appear in weather maps. That's seen here. If you look at the geopotential field, you can see that there's a clear trough associated with this large-scale wave motion. And in particular, look for the location of the low here. If you consider that there is cyclonic vorticity around the low, it's very easy to recognize that there's going to be an intensification of the trough associated with this wave and an enhancement of the corresponding ridge located to the east of the low pressure system. So this wave-like motion is very common in the atmosphere and is often driven by basically zonal inhomogeneities, such as topography, as we discussed in the vorticity section. So recall, what's the point of our analysis of quasi-geostrophic theory? We're looking at large-scale atmospheric behavior in the mid-latitudes, and the two particular features that we'll be looking at are large-scale waves and mid-latitude cyclones. So here our focus will be on the large-scale wave component. Looking at the quasi-geostrophic vorticity equation, recall that we derived a form of this equation which consists of right-hand side terms, including stretching, which is the first term on the right-hand side, and advection of absolute vorticity. We're going to expand this last term into advection of relative vorticity and advection of planetary vorticity, and for the time being, we're going to neglect the stretching term associated with the motion. So we're purely considering barotropic waves, that is, waves with no vertical velocity component. Consider now a large-scale upper atmosphere tropospheric wave. Here we have lines of constant geopotential shown in black, which exhibit very clear wave motion. In particular, the geostrophic wind here is denoted with the blue arrows, and recall that the geostrophic wind will be following along lines of constant geopotential. Hence, we'll be moving between these contours. We have upper atmosphere low and high regions associated with cyclonic and anticyclonic vorticity. So in particular at point A, we have cyclonic vorticity, that is counterclockwise motion around this low. At point B, we have anticyclonic or clockwise motion, and at C, we again have cyclonic or counterclockwise motion. So this corresponds to relative vorticities which are positive at A and C and negative at point B. So consider now the term that describes planetary vorticity advection. This term is simply minus Vg times beta. Recall beta here is the partial derivative of the Coriolis parameter f with respect to the meridional coordinate y. Well, if we break up our wave into two regions, one bounded by points A and B and one bounded by points B and C, we'll observe that the direction of the wind within these regions, either towards the North Pole or away from the North Pole, indicate the sign of the planetary vorticity term. So in the red region, we have that the meridional velocity is positive, that is towards the north, and that beta is positive. Hence, the planetary vorticity advection term, minus Vg beta, is going to be negative in this region. In the blue region, we instead have southward flow, so Vg is negative, beta remains positive, and as beta is positive everywhere on the Earth's surface, and hence the advection of planetary vorticity term, minus Vg beta, is actually greater than 0 in this region. Consider relative vorticity advection now. Relative vorticity advection is given by the dot product between Ug and the gradient of the relative vorticity, and the negative of both of those components together. So Ug will always be pointing eastwards, and the gradient of the relative vorticity will change, but will be purely aligned in the zonal direction. So in particular, note that since relative vorticity is positive at point A and negative at point B, we must have that the gradient of the relative vorticity points from this negative value towards the positive value, and hence points from point B towards point A. Hence, UG will be pointed in the opposite direction as the gradient of the relative vorticity, and hence hence in this region we have that the advection of relative vorticity term is positive here. In the blue region, we instead have that we continue to have that UG is eastward propagating, southeastward in this case. But we have that the gradient of the relative vorticity is now flipped. That is, at point B, the relative vorticity is negative, and at point C, the relative vorticity is positive, so the net gradient within that region must be positive and to the east. Hence, since these two vectors are aligned with one another in this regime, we will have that relative vorticity advection will be negative. That is, minus UG dot grad zeta will be negative in the blue region. So, comparing relative vorticity advection and planetary vorticity advection, we then observe that in the red region and the blue region, that planetary vorticity advection will have the opposite sign to relative vorticity advection. And in particular, in the red region, relative vorticity advection is positive, planetary vorticity advection is negative, and the opposite in the blue region. So consequently, these two terms actually end up opposing each other. If we consider the quasi-geostrophic vorticity equation, that means that these two terms will have opposite signs to one another. So this is consistent with the fact that we have this inherent balance associated with the system when we considered absolute vorticity over the mountain. That is, if you went too far north, you would have dominance of one particular term, which would lead to rotation in the flow, and hence hence a change of direction associated with fluid parcels in the flow. So the question then becomes, how does this competing vorticity advection affect the large-scale wave? Well, let's see here. So if in the red region we have positive advection of relative vorticity, then looking at the vorticity equation, we must conclude that in the red region, advection of relative vorticity tries to increase the vorticity here, whereas it tries to decrease the vorticity in the blue region. Since the vorticity maximum occurs at point A, that is the left-hand side of the red region, then any increase in the relative vorticity in the red region will lead to an eastward propagation of the wave. That is, the maximum associated with relative vorticity will tend to propagate to the right-hand side as relative vorticity within that region increases. On the other hand, in the blue region, we have advection of relative vorticity tries to decrease the vorticity in this region. So this leads to what is inherently a ridge in the flow, or that this leads to the ridge in the flow tending to propagate to the east as well, as the vorticity in the blue region increases, and the vorticity in the red region decreases, shifting the wave eastwards overall. The opposite tends to occur with planetary vorticity advection. In this case, in the red region, advection of planetary vorticity tends to decrease the value. So this leads to the red region exhibiting more ridge-like behavior associated with the wave, whereas the blue region exhibits more trough-like behavior. Consequently, you're going to see a westward propagation of the wave as the vorticity maximum transitions westwards, away from point C. And the vorticity minimum associated with point B transitions westwards as well, associated with a decrease in relative vorticity in the red region. So this is a bit tricky, and so I've put up a warning here in order to advise you. So advection of relative vorticity then tries to propagate the wave eastwards, whereas advection of planetary vorticity will try to propagate the wave westwards. So make sure you go over this a couple times in order to verify that you understand what exactly is going on with the evolving wave. Okay, so let's look at vorticity and geopotential. We have our vorticity equation here, again emphasizing the advection terms, advection of relative vorticity and advection of planetary vorticity. We know the form of the geostrophic wind in terms of the geopotential phi. It turns out that we can simply calculate the geostrophic vorticity by substituting in these values for the geostrophic wind and observe that the geostrophic vorticity is in fact only equal to the Laplacian of the geopotential divided by F naught. So if we assume now that the geopotential has a wave-like signature associated with it, that is, we have a background geopotential, which is a function of pressure. This is analogous to the T naught as a function of pressure that we assumed when deriving the quasi-geostrophic equations of motion. And we have a contribution of the zonal mean wind to geostrophic balance. That is, recall that the presence of a zonal mean wind will lead to the generation of Coriolis forces, which must be balanced by a corresponding pressure gradient term. And finally, we have a wave-like component, which is associated with basically the perturbation on top of this mean background flow. So the wave-like component is what we're primarily going to be interested in and understand how this wave develops over time. We have wave numbers k and l associated with wavelengths Lx and Ly of the wave, here defined as 2 pi divided by Lx as k, and 2 pi divided by Ly is going to be defined as lowercase l. In particular, note that increasing wave number then corresponds to decreasing wavelength of the wave. We can then use the geopotential in order to compute the geostrophic wind component simply using the geostrophic wind relationship, and we observe that the geostrophic wind in the zonal direction entirely looks like the mean zonal wind u bar plus a perturbation L times A times sine kx times sine Ly. The meridional wind, on the other hand, looks like k times a times sine kx times cos Ly. Here the meridional wind is roughly 0 in the background. So taking these two together then and using them to compute the geostrophic vorticity, we observe that the geostrophic vorticity is simply then given by minus k squared plus l squared times a sine kx times cos Ly. In particular, observe that this term has the same trigonometric variations associated with it as the geopotential wave that we had before. That is, we still see the sine kx times cos Ly term that was present in the geopotential. Here, however, we have the addition of the minus k squared plus l squared term. Now, ignoring the wave numbers for the time being, observe that taking the second derivative of this geopotential term simply leads to a term which is proportional to the negative of the original term, where the constant proportionality is simply going to be equal to k squared plus l squared, or the sum of the squares of the corresponding wave numbers associated with this wave. So for vorticity then, we have this formula that we've derived for geostrophic vorticity. We can now use this in order to compute the wave-like character associated with relative vorticity advection and planetary vorticity advection. So using the fact that relative vorticity advection is defined by minus ug dot grad zeta, we can plug in our known values for ug and zeta and hence obtain the formula for relative vorticity advection as ku bar, k squared plus l squared times a cos kx cos Ly. Planetary vorticity advection, on the other hand, looks like minus beta times Vg, or simply minus beta Ka cos Kx cos Ly. So if we now compare planetary and relative vorticity advection, we'll observe from the previous derivation that the cosine products both cancel out when taking the ratio, and so we simply obtain the relative strengths of these two terms. And in particular, we'll observe that the relative strength of these terms depends on wavelength due to the existence of that k squared plus l squared term that emerged from the relative vorticity advection. So the ratio of planetary vorticity advection to relative vorticity advection is then simply given by beta divided by the mean wind u times k squared plus l squared, or alternatively 2 pi over lx squared plus 2 pi over ly squared. So for short waves, we have that lx and ly are small. Taking the inverse of a small quantity then leads to a large value, and hence we observe that for short waves the denominator is large. Hence, relative vorticity will be dominant in this case, and with relative vorticity advection being dominant, the tendency will be for the wave to propagate eastward. For long waves, on the other hand, Lx and Ly are large, the inverse is small, and hence the denominator of this expression is small, leading to planetary vorticity advection appearing to be the dominant term. Hence, for long waves, advection of planetary vorticity is larger, and these waves will tend to propagate westwards, consistent with planetary vorticity advection. So, in summary then, we have short waves will tend to propagate eastwards, and long waves will tend to propagate westwards. Here we have a tabulated summary of short waves versus long waves. Short waves typically have strong curvature and hence large values of relative vorticity. This leads to emphasis of relative vorticity advection. Relatively small amplitude associated with relatively small changes in the Coriolis parameter from trough to ridge, and hence in this case we have advection of relative vorticity being larger than advection of planetary vorticity, and hence short waves will propagate eastwards. For long waves we have weak curvature, hence small values of relative vorticity. However, they have large amplitude due to the fact that they are slowly varying in space, and hence have relatively large changes in Coriolis parameter from trough to ridge. This leads to advection of relative vorticity being smaller than advection of planetary vorticity, and so the wave will tend to propagate to the west, again depending on the mean wind speed.